Next, I guess we want to think about many-to-one and one-to-many associations. Basically just the same thing, just depends on which direction you're reading it. Right? So if we read this from left to right, we've got many-to-one. If we read it from right to left, it's one-to-many. And so in this example, I'm looking at artists and paintings. So artists have an artist ID as primary key and also have attributes for their name and date of birth. And paintings have a painting ID or PID for their primary key and have a title and evaluation. And we've got the situation where for each artist there might be 0 or more paintings, but for each painting there's exactly one artist. Okay. So if we have a situation like this, how do we implement the association? And again, if I just look at, if I had just implemented these as simple tables without any association, then our painting table would have 3 columns, a column for PID, P1, P2, P3, P4, titles, Starry Night, Irises, Sorrow, Night Watch, and valuations. And our artist table would have artist IDs, A1, A2, A3, and names, Van Gogh, Rembrandt, Jones, and dates of birth. And in this case, just looking at an example of how this many-to-one works, we've got Van Gogh painted 3 different paintings that we have in our database. Starry Night, Irises, and Sorrow. And Rembrandt just has this one that we have in the database, Night Watch. For each painting, there's just one artist, but for some of the artists, there may be multiple paintings. So how do we implement that? Well, let's think about it. Can we just combine everything into a single table? And we can't. We can't, at least not in any reasonable way, because each artist can have multiple paintings. And so if we combined it into one table, each row of the table would have artist information and painting information. But if the same artist painted 3 different paintings, then we'd have to have 3 rows. And the artist information in each of those 3 rows would be the same. We'd basically be putting a lot of redundant information into the database. So we'd be recording that artist A1 was named Van Gogh and born on March 30th, 1853. We'd be recording that information 3 times if Van Gogh painted 3 paintings that were in the database. And obviously it could be a lot worse than that. What if an artist had 500 paintings? And what if we were storing more information about artists than just their name and date of birth? Maybe we were going to store their birthplace, their parents' names, how many children they had, who knows, where they were born, and so on. So we might have, lots and lots of columns, a lot of information about each artist. And if we combined all this into one table, then we'd be repeating all that information for every work of art that they did. So a single table doesn't work in this case. There'd be way too much redundancy. We'd waste a ton of space. Files would be much bigger than they had to be. That would make everything very slow. Okay, so basically a single table solution is not viable. Could we include for each painting, could we include along with each artist the painting ID of their painting? And the answer is no, right? Because each artist can have many paintings. So again, we would need to duplicate the artist info for each painting with a different foreign key in each row. It's basically the same problem as before, right? That since we don't want to repeat all the information about a particular artist for every painting that they did. And we'd still have to do it this way. with that kind of foreign key approach. How about we do the foreign key approach the other way and include the foreign key for artist, that is the artist ID, in the painting table. And that works because for each painting there's just one artist, right? So we don't have to list the same painting more than once in the table with different foreign keys for different artists, because each painting just has one artist. So this works, right? So since there's only one artist per painting, we can include a foreign key to refer to the artist's works. And the last possibility, can we create an additional table to implement the association? And the answer there is yes, we can do that. And in fact, this solution can always work regardless of what the multiplicities are. We can always just create a table just for the association. Okay, so let's take a look at the different possibilities here. So in this case, we really just have two possibilities. Single table doesn't work. Of the two different ways that we might think of doing foreign keys, there's only one of them that works, not the other. And then we can have the add an extra table approach, which will work. So in this case, if we're going to add a foreign key to one table, well, the way we want to do this, right, is because for each artist there can be multiple paintings, we don't want to add painting ID to the artist table. Instead, because for each painting there's just one artist, we can add a column for the artist ID. And that's what we've done here. So Starry Night, Irises, and Sorrow were all painted by Van Gogh. So here's our extra column that we added for our foreign key. And in each of those rows have the same foreign key that I'll say point. Remember, it's not really a pointer, but point to the row for Van Gogh in the artist table. And then the painting Night Watch was painted by Rembrandt, so we store in the AID column of the row for Night Watch the artist ID for Rembrandt A2, which essentially points to this row. Okay, so that works. And alternatively, we can add a table. If we take the approach of adding an extra table, then that table, here I've just called it artist painting. Maybe we could think of a better name. But this is going to tell us which artist painted which paintings. And notice that because there's at most one artist per painting, each painting ID will only occur once in the artist painting table. Right? And there's going to be a one-to-one association between artist painting records and painting records. And on the other hand, because the same artist can paint multiple paintings, we can have more than one row in the artist painting table with the same artist ID, but different painting IDs. So we see that painting P1, P2, and P3 were all done by artist A1, who is Van Gogh, whereas painting P4 was done by artist A2, who was Rembrandt. Okay. And so since in the artist painting table, PIDs are unique, right? We never have this same painting associated with more than one artist. Painting ID works for a primary key for artist painting. On the other hand, AID, this is not a suitable primary key because the same value is in multiple rows. Okay. And so again, remember how we do our schemas here. If I'm asking you for one of these, just as a reminder that we have the name of the table, a list of attributes in parentheses, and primary key attributes are underlined. All right, so for the artist painting table, the primary key is going to be PID. Okay. All right, so we looked at one-to-one, many-to-one. Last thing, I guess, in terms of associations that we have to look at are many-to-many associations. So here's a typical example of that. Suppose we have students who have student IDs as their primary key, and they have names and majors. And we've got courses that have a course code as their primary ID, primary key, and a title and a description. And we have an enrolled in association to indicate which students are enrolled in which courses. And this is many to many, right? Because a particular student can be enrolled in 0 or more courses, and a particular course can have 0 or more students enrolled. So we've got this kind of many to many situation. And here's just as an example down here, maybe we've got Fred and Sally who are computer science majors, and Bill is a math major. And Fred and Sally are both taking CIS 452, and that's the only course that either Fred or Sally are taking. And on the other hand, CIS 452, in addition to Sally and Fred being in that course, Bill is also taking CIS 452. And Bill is also enrolled in CIS 180 and CIS 440. And kind of a lot of computer science courses for a math major, I guess, but anyway. So now we've got to think about, how can we implement that association? And I guess we can think about the same kinds of solutions as before. Sorry, I shouldn't have done that. Can we put everything in one table? No, because same kinds of reasons as before, because each student can be associated with multiple courses. If we put it all in one table, then the student's information would be redundantly recorded in the table for every course that they take. And likewise, the information about every course is going to be redundantly stored in the table for every student that takes that course. And so this would be terrible, and we certainly can't do that. So a single table is not viable. Also, the foreign key solutions are not going to be viable either, for the same reason. So if with each student, instead of putting it on and storing the course information with it, we store just the primary key of the course, there's still a problem, right? Because if Fred is, well, let's say, actually, I'll be more realistic. If Bill is taking 3 courses, it doesn't matter whether I store the whole course record or just the primary key for it. Either way, if Bill takes 3 courses, I'm going to have 3 rows for Bill, each with a different primary key value, a different course code value. And if that's the case, then all of Bill's information is going to be recorded 3 times, basically. And again, in this example, maybe that doesn't look so bad because we've only got just name and major are the only real attributes and SID that we're recording about a student. But in reality, there'd be a lot more attributes, right? And they'd all be stored redundantly. So in addition to Bill's name and major, we'd have his email address, snail mail address, phone number, and advisor, on and on. So we probably have many, many columns in there, and all that information would be redundantly recorded over and over again for each time that student enrolled in a course. Right? Okay, so the foreign key solutions don't work. I won't go through the argument as to why we can't store a student ID in the course table, but it's for exactly the same reason. It would mean that the information about each course would be duplicated in the database for every student that enrolls in that course. Okay, so that leaves us with only one possibility, which I gave away earlier. Right, the only solution is to add a table for the association. And so we're going to have a table, separate tables, one for student with all the students' information, a table for courses with the course information, and a third table, here I've called it enrollment, that tells us which student is enrolled in which course. So for each enrollment, there's a row in this table. And if we notice, here if we're thinking about primary keys, notice that we can have the same student ID can appear in this table more than once. So for example, Bill is taking 3 different courses, so Bill's student ID appears in this table 3 times. And also, there are 3 different students who are taking CIS 452, Sally, Fred, and Bill. And so we've got the course code CIS 452 recorded in here 3 times, once for each of the students that's taking it. So student IDs in the enrollment table are not unique, and course codes in the enrollment table are not unique. So neither one is going to be a valid primary key. Right? So, but what is unique is the combination of the two. Right? We're never going to record in this table more than once that Fred is enrolled in CIS 452. Right? And we're never going to, so we're never going to record more than once that a particular student is enrolled in a particular course. Of course, we could have a slightly, so in this example, we're only storing in the database current enrollments. More realistically, we'd probably store historical enrollments and the grades and other things. And so we might have an enrollment table that had SID, course code, and term. And in that case, the same student, we might record being enrolled in the same course in 2 different terms because they retook the course or something like that. So anyway, if that were the case, we'd have to think again about exactly what the primary key would be. But I think that's pretty much what we need. Okay. Okay, so I think I'm going to, well, yeah, I'll just go ahead. I'll maybe, I might edit this into shorter videos later. Okay. Last thing I guess that we really need to look at is how to deal with inheritance. And we've got a number of possibilities how to deal with inheritance as well. And so here's an example where we've got maybe we've got a conceptual model where we have people or persons with social security number as primary key and names and date of birth as attributes. And we've got a couple of subclasses of people, students who, in addition to social security number, name, and date of birth, also have a major and a GPA. And maybe we've also got instructors who, in addition to social security number, name, date of birth, have an office and a department. So we've got students and instructors that inherit from person. And maybe we have TAs that have the characteristics of both students and instructors. So TA inherits all the attributes of students and all the attributes of instructors, and maybe also has a supervisor that we were going to record. And notice, by the way, that I guess, well, I'm not sure this is true. We use Java as our primary programming language here, and I'm not sure if that's everybody's primary language, but at any rate, this model, as we've constructed it, can't be directly implemented in a language like Java that doesn't support multiple inheritance. Right, so this idea we have TAs inheriting from 2 different classes, you can do that in C++ and some other languages, but other languages you can't. But anyway, that's beside the point, because we're not going to be doing that anyway. We're going to be trying to figure out how to turn this into tables, not how to implement it in Java or C#, C++ or whatever. Also, yeah, I just wanted to point out that notice that all of these classes have social security number as their primary key, right? Because this SSN is inherited either directly or indirectly in every class. And so if SSN uniquely identifies every person, then clearly it identifies every student or instructor or TA, because they're all people. Okay. So as an example here, let's suppose that we've got a number of different people that need to be recorded in the database. Maybe we've got a librarian named Wilma, and she's got some birth date and social security number. And we've got Bill, who's a student majoring in math. I'm not going to go through all the data here. And Sally is a professor. And Fred is a student and works as Sally's TA. Okay, so we've got basically one person that kind of fits each of these four categories. We've got one sort of generic person, the librarian, who's neither a student nor an instructor nor a TA. We've got one person who's a student but not an instructor. We've got a professor, Sally, who's an instructor but not a student. And we've got one student who's also a TA, so is both a student and an instructor. And there's a couple different ways that we can go about this. Again, we still have some choices. And if we're thinking from the object-oriented perspective, where in object-oriented programming, every object is an instance of one particular class, then if we're thinking that way and we follow that approach, then we're going to record each person in exactly one table. And so in the person table, we'll record the social security number, name, and date of birth of any person who's not one of the subclasses, any kind of just generic person who's not a student or an instructor or a TA. Students who are not TAs will get recorded in the student table. And we'll record there their social security number, name, date of birth that they inherit from person, and as well as their major and GPA. And instructors who are not students will get recorded in the instructor table. Right? Their social security number, name, and date of birth that they inherit from person, and then their office and department. And TAs, who are both students and instructors, will be recorded in the TA table. And there we'll have all their inherited attributes, social security number, name, and date of birth inherited from person, major and GPA that are inherited from student, and office and department that are inherited from instructor, and then supervisor, which is unique to the TA class. If a class in the UML model is abstract, then we don't need a table for it. So for example, if the database doesn't have generic people, like Wilma the librarian, then the person class would be abstract, and we wouldn't need to create a person table. And if we didn't have any generic people, we could get rid of that one. So here's what this example would look like. We'd have these four tables: person, student, instructor, and TA. And with these four people, each table would get just one row in it. We'd have Wilma would be recorded in the person table, and Bill, who's the student that is not a TA, would be recorded in the student table. And Sally, who's a professor and not a TA, would be recorded in the instructor table. And Fred, who's both a student and an instructor, because he's a TA, would be recorded in the TA table. Okay, so that's sort of the way our data would end up being organized. If we think from the ER perspective, even though the concepts are very, very similar, there are some subtle differences. And in ER modeling, we have entity sets instead of classes. And when we're thinking about sets, it's perfectly natural to consider the same entity to be a member of more than one set. Right? Sets can overlap. And so following this approach, we might record the same person in more than one table. And so what we're going to do here is that we're still going to have these 4 tables, but each table is only going to have the primary key attribute, social security number, and the attributes of that class, and not the inherited ones. Right? So the person table is going to look the same as before. We'll have the social security number, name, and date of birth. The difference is that in the person table, we're not going to record just generic people like Wilma, the librarian, but we're going to record every person in the person table. Right? So the person table is going to contain everyone's name and date of birth. And in the case of a student, that student will be recorded in the person table, and then they'll also be recorded in the student table. And the student table will supply, well, we need the social security number because that's the primary key. But aside from that, just the major and the GPA, and not the inherited attributes of name and date of birth, because their name and date of birth will be recorded in the person table. Likewise, instructors, in the instructor table, well, instructors will also be recorded in the person table. That's where we'll record their name and date of birth. And in the instructor table, we'll just record their office and department. And in the TA, in the case of a TA, the TA is going to be recorded in all 4 tables. We'll record their name and date of birth in the person table, their major and their GPA in the student table, their office and their department in the instructor table, and their supervisor in the TA table. Okay, so what we're going to end up with then, in this example, we've got these 4 people. Every single one of them is going to be recorded in the person table. So that table is going to have 4 rows now instead of just the row for Wilma. In the student table, we've got 2 students. Bill and Fred are students, and so they're going to be recorded with their majors and GPAs in the student table. Sally, the professor, and Fred, the TA, are instructors, so they'll be recorded in the instructor table with their department and office information. And then Fred, the only TA, will have his supervisor's number recorded in the TA table. So so this looks quite a bit different, right? So this is how our data is going to look if we take the ER approach versus this using the OO approach. So let's consider kinds of advantages and disadvantages here. And again, there's not going to be any way that we can say that one of these is better than the other without considering what the actual data is and what the actual queries that are going to be executed are. So, for example, suppose a typical query is going to be to find the names of everyone born before 1980. Well, in this case, the ER approach is going to be much better because it requires a simple query against the person table. But the OO approach requires searching all 4 tables. Right, let's just look again. Right, we want to find names of everyone born before 1980. In the ER approach, the name and date of birth of every person is just in one table. So that makes we just have one table to look through. In the OO approach, we're trying to find names of people born before 1980. Well, I got to check the person table, and I got to check the student table, and I got to check the instructor table, and I got to check the TA table, and I've got to search 4 different tables to find the same information. And so, for this kind of query, the ER approach is going to turn out to be much better. On the other hand, suppose we want to find the names of all the TAs who work for the CIS department. In this case, the OO approach is going to be much better, right? Because if we're trying to find TAs who work for the CIS department, well, here we can we see that a particular person is a TA, and we see who their supervisor is. But then we've got to join this with the instructor table to see who, to match the supervisor number to some instructor and see what department it is, right? So, oh wait, and we want the names of the TAs, not just to find the TAs. So since we need their name, we need the people table to get the name. So we've got to basically join the TA table to the instructor table to figure out who they work for and what department they're in. And then furthermore, we also have to join, so we're going to match the supervisor number to here. We also have to match the social security number to here to see that what the person's name is. So we've got to join, we've got to perform 2 join operations, and that's expensive. On the other hand, if we use the OO approach, then we can just go through the TA table without having to do any joins, and we can find the names of the TAs who work in the CIS department very easily. Okay, so we've got the same sort of situation as when we were looking at different possibilities for how to implement associations. We've got different ways of doing the inheritance, and there's no obvious best way without stopping to think about what kinds of queries are going to be run and how often they're going to be run, and so on. Okay. Oh, and by the way, as long as, well, yeah, as long as I'm talking about that. So this is one of the reasons why it's not a good idea to start designing by trying to decide what the tables should be, right? It's much better to first develop a conceptual model so you understand what the concepts and associations are, you understand what kinds of data has to be stored, and then as a separate design step, you can start to think carefully about how to implement each association, how to implement the inheritance on a case-by-case basis in order to do it the best way. And you need to have a very good understanding of what you're building before you can do that well. So at the time when you're first understanding the problem domain, that's not the time to do that, right? You're not going to know at that point probably, you know, am I going to run this type of query more, or am I going to be running this type of query more? Another possible way to implement inheritance is by using a null value approach. And so in this approach, what we're going to do is we're going to use just one table for all of the entities in the same inheritance hierarchy. So in the example, basically we're going to have just one table for all the people, regardless of whether they're students or instructors or TAs or just generic people like a librarian or janitor or whoever. And so in the example, we have a people table and supply null values for major and GPA for people who aren't students. And we supply null values for whatever it was, office and department for people who aren't instructors. And we supply null values for supervisor for people who aren't TAs. If null values aren't sufficient to determine the class of a person, we might need to add an extra column, like call it type or something, to record the class by using values like person, student, instructor, or TA. So for example, if supervisor is null, does that mean that the person's not a TA, or that their supervisor is unknown, that we don't know who their supervisor is, or they haven't been assigned a supervisor yet, something like that. So in this case, Combining everything into one table, we'd still have Social Security number as primary key. We might have to add a column called type to indicate what type of person it was that we were recording. Some cases we might not, depending on, maybe we can determine that from seeing what values are null. And then we have all the other columns for name, date of birth, major, GPA, office, department, and supervisor. And if we were to implement this for the example that we were given with these 4 people, well, we're going to have one row in this table for each person. Wilma, the librarian, will simply have null values for major, GPA, department, office, and supervisor. Right, those are the student, instructor, and TA attributes. And Bill, who's a student but not an instructor or a TA, will have null values for department, office, and supervisor. And Sally, who's a professor, is going to have null values for major and GPA and a null value for supervisor, but will have values for department and office. And Fred, who's a TA, is going to have values in all the columns. So if we think about advantages and disadvantages of this kind of one table approach compared to the 2 other approaches we've looked at, one advantage is that all the queries involve only one table. So that means that we're never going to have to perform any join operations to retrieve information from that table. So that's the advantage. For those queries where we would otherwise have to do a join or multiple joins, then this may be a good solution. Disadvantages are that the null values may end up wasting a lot of disk space. And also, the more important issue with that, with wasting the space, disk space is cheap. But the bigger concern isn't the cost of the disk space, it's the fact that the files are going to be bigger, potentially, and that means it's going to take longer to scan them to solve queries. And related to that is the fact that because we just have this one big table, every query that we run is going to involve this large table that could require a lot more disk I/O to process. Because it's going to be a bigger file than if we had split it up into multiple smaller files. Okay, so again, there's advantages and disadvantages to each approach, and so this is a significant part of what design is about. All kinds of design is weighing trade-offs and trying to choose the solution that it's not going to be perfect for everything, but will give you the overall best solution. And so again, just as a couple of examples, of null value versus the OO and ER approach. Let's suppose we, for example, wanted to find the names of everyone born before 1980. Well, the null value approach is going to be worse than the ER approach because we have to look through a much bigger table. But the no value approach is going to be better than the OO approach, since in the OO approach we'd have to search 4 different tables. So it's sort of in between those 2. And let's look at another example. Find the names of all the TAs who work for the CIS department. Well, now the null value approach is worse than the object-oriented approach, since again we need to search through a much larger table. But the null value approach in this case is better than the ER approach, since the ER approach requires joining 3 tables. So again, we have still, it's the same situation as always. We need to consider exactly what the queries are going to be. It may be sometimes the job of a database administrator to kind of monitor this even after the application is in production. And if it turns out that in practice your users are executing parts of your software that are running queries, certain queries more than you expected, and running other kinds of queries less than you expected, may turn out that you didn't really make the right trade-offs. And so it might be that you need to rethink it and change your design. It would be unfortunate because that can be a fair amount of work if you've already gotten into production, you've already written code to access the database and so on. But that's one of the things that you might need to watch out for in a real-world practical situation. Okay, well that wraps up what I wanted to say about this process of kind of translating conceptual schemas into relational schemas.